Hi, and welcome to the lecture for section 1.1, the first content lecture for Math 232. This lecture is about vectors in R2 and R3. So I'm going to do this actually probably most of the lectures, and it will usually appear at the top of my lecture notes. So there'll be some vocabulary. I will strongly encourage you to learn the vocabulary. A good portion of getting a handle on linear algebra is to learn the specific meanings of all the words. There's going to be probably a lot of new words. And when you clearly understand what those words mean, it makes it much easier to understand what's being asked of you, to understand what I am saying. So I am going to just go through the vocabulary here at the top, and I'll be pointing to vocabulary throughout all of the lectures. So here we are, this symbol here, R2. I'll be reading that R2. That basically means two-dimensional space, a flat plane, like a piece of paper extended indefinitely, R2. Then we have R3, that is three-dimensional space, and that's where we're going to stay for this lecture, but it's probably not too much of a leap of your imagination to imagine that we can have R4 or R5 or etc., whatever we like. So we can extend this to a higher dimension. Okay, then we're going to have this thing here, an n-tuple. So an n-tuple means an ordered list of n numbers enclosed in brackets. So here, for example, is an n-tuple where n is 3. And here, and sometimes we would even call that a 3-tuple. Or here is an n-tuple when n is 2. And sometimes we would call that a 2-tuple. Okay, so that's an n-tuple. So the coordinates, we use the word coordinates, and the coordinates, we're thinking of that as the n-tuple that describes the position of a point. So if we were in R2, this describes the point where x is equal to 2 and y is equal, when x is equal to 5 and y is equal to 7. If we are in R3, then this 3-tuple would describe a point where x is 2, y is 3, and z is 4. So that's the coordinates of a point. The word scalar. The word scalar means an object that is described entirely by a number. So let's give a physical example of this. Temperature. Temperature is described solely as a number. It is whatever, minus 3.2 degrees, or it is 52 degrees. Whatever that Celsius say, whatever that is, that number completely defines what the temperature is. That is in contrast to what we're going to be concerned with in this course to a very large degree, and that is vectors. So vectors are different from scalars in that they have a number associated with them, which we call the magnitude, but they also have a direction associated with them. So one example of that would be, say, velocity. So you are going 10 kilometers per hour heading east. So not just to understand exactly how the object is moving, you need to know how fast is it going, its speed, that is a scalar, the speed, but you also know in what direction. And the combination of the speed plus the direction gives you the velocity vector. Okay, so there's two things that you're describing the vector by: its magnitude and its direction. And then when we use the word component, we mean each item of a vector. I'll point that to the components when we draw the vectors below here. Okay, so these are important words. So what I encourage you to do is just when you're reviewing, go through them. Maybe don't look at the definition, cover the definition, say R2, do I know what that means? R3, do I know what that means? Vector, do I know what that is? And be able to actually get the definition out clearly yourself. And if you can do that, then great, then you'll always know what that means. Okay, so we have a way of graphically representing points and vectors in R2 and R3. Sometimes can be a little bit of confusion based on context. I'll try to make that clear here. So let's first look in R2. R2 is two-dimensional, and we will typically draw R2 like this, we will have here an X and a Y component. Sometimes we call it X1, and like sometimes this axis could be called X1 and this axis might be called X2. Sometimes the axes are called X and Y. It depends. I mean, let me just put the three-dimensional equivalent here so I can make this hopefully clear. We could have another coordinate system. We have the three, so this is R2. Now I've drawn the R3 coordinate system here. In R3, we will often label this X, Y, and Z. This is our right-handed coordinate system. And then we will sometimes label this one X1, this one X2, and this one X3. I think you can possibly see why I'm doing this, and that is because when we go to R4, we ditch the XY and XYZ that we're sort of more used to from our elementary algebra. So what we do is then we move to X1, X2, X3, X4, X5, say for a five-dimensional thing. So we're going to be in this course often looking at R2 and R3 first, just like we're doing here. And then we're going to see how it naturally extends up into higher dimensions. So just be aware of that. Sometimes I'll refer to the first coordinate as the X coordinate and the second coordinate as the Y coordinate. Sometimes I'll refer to the first coordinate as the X1 coordinate and the second coordinate as the X2 coordinate. Okay, if we have a point, well, let's take a point. Let's take a point here. I will often label this way: the point with coordinates 2, 3. So this is a point defined by the n-tuple 2, 3. Okay, the X coordinate is 2 and the Y coordinate is 3. Okay, that's you should be completely familiar with that. Now, how are we going to expand this up to include the vectors? It's going to look very, very similar. We're going to be here. We're going to have 2 and 3, say, and we're going to put a point at 2, 3. There's the point at 2, 3. But then what we're going to do is draw a line from the origin to the point. And we'll put an arrow on there and it will stop there. And then we will call this the vector P, and it will be written this way. Now, there is going to be potentially a little bit of confusion that you're going to have to sort out with context, because that is a way to write the vector P 2, 3. Sometimes because it's a hassle to write it vertically, sometimes because different textbooks do different things. Sometimes we will write like this, in which case there can be a little bit of confusion of, do you mean a point or do you mean the vector? And so this thing here is indicating that it's a vector. In the textbook, you'll see that vectors are bolded. I can't bold very easily, so I put the little arrow over top to indicate that is a vector. So either one of these representations is the vector 2, 3. Is the vector that has X coordinate 2 and Y coordinate 3. Sometimes if you just see something like that looks like this, you're not sure, is it a vector going from the origin to 2, 3, or is it actually the point 2, 3? Generally, then what you have to do is tell from the context. Okay, let's just do one example in R3. We need to have that there. I'll just make a little bit more space. There we go. We're here. So we've got X, Y, and Z, and I'll put a point here, and I'll give it some coordinates, and I'll draw a line to it from the origin to the point, and I'll label that as a vector Q, and Q in this case is my vector 0, 1, and a half. Means that it has X coordinate of 0. So this thing right here is telling me that X is 0, Y is 1, and Z is 1/2. That is a 3-tuple. It describes the terminal point of the vector. Okay, just again, a note on notation. We will typically be using letters to indicate scalars which are not bolded or do not have the vector sign over them. And then when we want to indicate a vector, in the textbook, you will see they are bolded. And because that's difficult, as I said, I will be putting like this. I'll probably go more like that, or I could go like that. But either those are equivalent. So I'm indicating that I'm thinking of that quantity as a vector. If I just write this, then I am thinking of whatever that is as some type of a scalar. Okay, let's just talk about the orientation of a vector and whether two vectors are equal. So two vectors are equal if they have the same magnitude and direction. So let's just, they don't have to be oriented at the same place on the coordinate system. So if I was to have here, let me just make an example of this, and we're gonna see this coming in the example below as well. But if I was to have this vector here, let's just make it pretty easy. There it is, 2, 1, and I called this the vector v with x coordinate 2 and y coordinate 1. Now, if I shuffle that vector up somewhere else, like even over here, say, for example, I'm trying to make a vector that it looks exactly the same. So that the second vector that I've drawn is, just change the color here. It is, that, sorry about that. Hang on a sec. I don't know why the notifications has come up. Let me, oh, you can't see that. I've got a notifications thing come up on my screen. Let me just make that go out of the way. I don't know how to get rid of it. Just give me 2 seconds here. Sorry. There we go. Okay. So I have now drawn a second vector here. Now, given that if I've been to the length of the ability of my drawing, if this length is the same, that is the magnitude. Okay. The length is the same and they are parallel to one another. So they're in the same direction. So from the perspective that we are always going to deal with here, these two vectors are the same. They have the same length and the same magnitude. It doesn't matter that one of them is sitting over in the second quadrant and the other one is sitting in the first quadrant. Okay, so that is something to make sure that you're aware of. We can always, in some sense, move the vector and attach it to the origin. Okay, so how do we add these guys up? Here we've got two vectors, v1 and v2. There they are. And if we wish to add them, we'll do this both geometrically and algebraically. So let's put over here what those vectors are. v1 is the vector 2, 1, and v2 is the vector 1, 3. Okay, make sure you can do that. I mean, all I'm doing is reading the coordinates off of the drawing. Okay, so you should be able to do that. Algebraically, they're super easy to add together. You just simply add the components. v3, which is going to be v1 plus v2, and that is going to be v1, there it is, 2, 1, plus the vector v2, which is 1, 3, and I add the x component, 2 plus 1, and I get 3. I add the y component, 1 plus 3, and I get 4. So the sum of v1 and v2 is v3, and that is the vector 3, 4. I can also show you what that looks like geometrically. And this is something else I'm going to emphasize as the course goes along. We're going to be doing stuff algebraically, and then we're going to think, what is this meaning? What does this mean if I look at a picture of what's going on? And I encourage you to ask yourself that question frequently, because seeing what's going on often makes it really easy to solve a problem. And then you can work out the algebra later. Okay, so in this case, what do? I make a copy of v1. So there's v1 right there. I make a copy of v1 starting from the tip of v2. So I draw that right here, and it's right here. So there I make a copy. So right here, this is a copy of v1. It's still v1 because it's the same magnitude and same direction. So it's still v1. And so I've got the copy there. And then what I do is I draw a new vector from the origin to this point right here. So I draw that vector right there. There it is. That is the vector v1 plus v2. And you can do it the other way too. I can make a copy of V2 right here. That will obviously work. Okay, so that's a copy of V2. So you can do it either way. So you can add them up geometrically, you can add them up algebraically, and of course you'll see that the black vector here, V1 plus V2, that is V3, and you can look here at the coordinates and you'll see that it is 3, 4, which has to, and luckily does, match what we have right here. So there's the 3, 4 there and the 3, 4 there. Okay, that's how you add. How do we take a negative? Well, a negative is parallel and in the opposite direction. So here's a V1. Now you notice that this V1 is not oriented at the origin. So if we want the negative of V1, we have to be careful about how we specify this algebraically. So this thing here is V1. Now geometrically, negative V1 is in the opposite direction, same magnitude. So I can easily draw that opposite direction, same magnitude. So let me just draw that. So I'm going to draw something that says same, opposite direction, parallel opposite direction, and of the same magnitude. So I draw that there. So this guy right here is a drawing of minus V1. Okay, minus V1, how about I call that V2? Now let's think about how to do this algebraically. First, I have to write out the components of the vector V1. Now, what are the components of the vector V1? Maybe stop the video and figure that out. So they are the change in the X direction. Let me get a different color here. There's going to be a change here in the X direction. And the change in the X direction there is 2. And then the change here from the initial point here to the terminal point here. Then the change in the Y direction is 1. So V1 is the vector 2, 1. And V2 is minus V1. And that is the vector minus 2, minus 1. It's easy to take the negative of a vector when you have the vector written out in this format here. You simply put a negative sign in front of each of them. You're multiplying that minus 1 onto both components. The only caution that's required here is noticing that it's not attached, if you will, or the initial point is not at the origin, and then making sure that you get the components proper as a result of that. All of the vectors in this course, we're going to be thinking of them as basically starting from the origin. So they're all going to be basically from the origin, but you just have to watch in case one is not, you may have to rearrange. But other than that, almost always they'll be starting from the origin. Okay, scalar multiplication. So again, when we're doing this sort of thing, we're thinking to ourselves, okay, we've got the word here, scalar. We just remind ourselves what that is. Scalar, it's a number. Simply a number. So we're thinking, okay, we're going to multiply a vector by a number. And so here we've got a vector V1. There it is, V1. And we're going to, let's just multiply it by 2. So we're going to do, let's write out what the vector is. We'll do that over here. V1 is the vector. I can see that the X component is 1. And the Y component is 2. Now I'm attempting to calculate V2, which is going to be 2 times V1. Okay, I'm over here. What I do is I am imagining scaling this vector by a factor of 2. So it's the same direction and its magnitude is twice. So I draw that there. So this thing right here, all the way to the origin, this thing here is 2 V1. I sort of obliterated V1 in this process. V1 is this guy here. Okay. So here, all I do when I take a vector, this guy here, I multiply it by a scalar, this guy here, I simply multiply each of the components, 2, 4. A vector is twice as long in the same direction. Okay, So that is adding, negating, and scalar multiplication. The next thing we'll do is subtraction. So because we've done negation, all we're going to be thinking of subtraction as the addition of a negative. Okay, so this is subtraction is basically adding the negative. So let's get an example here. Let's draw two vectors. Let's draw V1 right here. There's V1. I'm going to make this here 2 and this guy here 1. So V1 here is the vector 2, 1. I'll draw a second vector. That'll be, I don't know, the vector, let's see, 1 and 1, 2, 3, 1, 3. There's V2. Okay, so V2, the blue one, is the vector 1, 3. Okay, if we wish to subtract, we will subtract V3. We'll form V3 by subtracting V2 minus V1. Okay, and algebraically, this is very simple. We take here V3, we take V2. What is V2? That was 1, 3. And we add negative V1. V1 is 2, 1. Okay, I'm just sort of doing this in gory detail. Presumably, some of these steps could be done in your head. Okay, so we can figure out what this thing is. That becomes then -1 and -2. Oh, sorry, -1 and 2. 3 minus 1 is 2. There we go. Okay, so we know what the answer is. Now let's see geometrically what this looks like. We'll take V1 and we will form minus V1. Okay, so we take V1, that is the black one is V1, and we form the vector minus V1. So the minus V1 should be in the same parallel and in the opposite direction, same magnitude. So this right here is minus V1. Now we're going to add that to V2. V2 is the blue vector. So we're going to take this thing here, this guy V minus V1, and we're going to just move the initial point up to here. And then we're going to put that there like that. So that is, now we've got here, we've got V2. And right here, we've got minus V1. That's what we want, right? V2 minus V1. And then the resultant vector is this guy right here. Right there. There he is. And that is the vector V3. And we've computed out what that is. So we know, in fact, that this is -1 and this is 2. So we try to draw a nice picture, but what we're doing is when we do this geometrically, we take the first vector, we take the negative of the second vector, we take that second vector, the negative of that second vector, and we put the initial point of that one onto the terminal point of the first one. Okay, so we have a geometric interpretation of that as well. There's no need to do this in order to get this number if you have your vectors as components. It's clearly faster to do it algebraically. However, cannot emphasize enough that you want to have a picture in your head about what's going on. We're going to as this course goes, we're going to be projecting these things. We're going to be rotating them. We're going to be doing lots of fun stuff. And we want to have a picture in our head about what is going on. Okay. So vector addition and scalar multiplication have properties associated with them. Those are listed here. You should go through them and just maybe grab yourself an example. Like you could just take U is equal to 1, 3, and I try to use the square brackets to be 1, 3, and V is equal to 4, 10, something like that. If you liked, then you could make an example of this, U plus V, and you could form that as being 1 plus 4 and 3 plus 10. And then you could go V plus U like that, and that would be 4 plus 1 and 10 plus 3. And you could then confirm this property here. It's not a proof, It was, okay, we don't prove by example, but it is a way of just demonstrating to yourself what these properties are. These properties are true. Okay, and you can just run through with examples, just sort of making sure you understand what the property is, what you're being told. This is by no means is this a proof. This is just an example of something that's you're already being told is true. And I'm going to just highlight this one. When this thing where it says the order doesn't matter, so it doesn't matter if we add u plus v or we add v plus u, or we can switch the order and the result is the same. That property is called commutativity. So these two, addition is commutative. Vector addition is commutative. Okay, that's what this is. So let's write this down. This is commutative. This one I'm highlighting because we are going to see in this course, and maybe you will see for the first time coming, things that are not commutative. And that is actually a big moment. And it's a big moment and it has lots of implications. So I'm highlighting this property that, like you're used of, the order here does not matter. Okay, the second one here, this is associativity, and then there's a whole bunch of other properties here you can look through. They pretty much follow from what you're used to with regular arithmetic. So go through those with some examples and make sure that you're happy with them. If you're not happy with them, let's bring that up at the Zoom session and discuss why they are like that. Okay. Next thing is linear combination of vectors. This is really important. We're going to be using this repeatedly throughout the course. So again, highlighting the meaning, this word linear combination. So making a linear combination of vectors means to take some number of vectors and add them together, possibly also multiplying some of the vectors by scalars. Okay, we'll see an example. Okay, so what does it say here? We have some vectors here, v1, v2. We have some number of vectors, and we multiply potentially by scalars. The scalars could be 1, so you wouldn't see them there, but we can multiply by any scalar. We have some number of vectors, and we add them all together. We multiply v1 by some constant scalar number. We multiply v2 like that, and then we add them all together. And then we get a new vector, w. And we call W the linear combination of V1, V2, all the way up to VK. Okay, so whenever I use that term, W is a linear combination of V1 and V2, say, then you should be thinking, okay, it is a vector that results from adding those two together, where each of the vectors potentially multiplied by a scalar. Let's get some examples. Sometimes easiest to see something by example. So let's do an R2 example. Okay, here we are in R2. That means vectors have two components. Okay, so let's have vector v1, 1, 4, and vector v2, 3, 4. Okay, there we have two vectors. Let us form a linear combination. I'm going to call that W1. W1 is going to be 2 times 1, 4 plus 3 times 3, 4. So this gives you a chance to practice your scalar multiplication and addition. So that's 2 plus 9. That is 11 for the first component, and 8 plus 12, which is 20 for the second component. So W1 is a linear combination of V1 and V2. Okay, here's another example, W2. W2, I'm going to say it's minus 3 times 1, 4 plus 1 times 3, 4. And that's going to be equal to minus 3 plus 3, which is 0, and minus 12 plus 4, which is minus 8. So W2, this vector right here, is also a linear combination of V1 and V2. Okay, it doesn't have to only have two vectors here. We could have more. We could have, for example, W3. Here's a vector, and it's going to be a linear combination of V1, of V2, but not just of V1 and V2, also of some other vectors. Maybe I would have called this V3, and I would have called that V4. Okay, so now I've got W, I've got 4 vectors in R2 because they all have 2 components. And I can add them together after multiplying by these scalars that are sitting here in front. Okay, so I go ahead and perform that. And I get this number here, I hope, if I've done the arithmetic properly. And that vector W3 is a linear combination of 4 vectors. Okay, in R3, it's exactly the same. I'm just going to do one quick example, but it just scales up. We could have V1 equal to something like this, 1, 1, 6, and V2 equal to something like this, 0, 1, minus 3. Okay, there. I know that these vectors, V1 and V2, are in R3 because they have 3 components. They have an X, Y, and a Z component, or possibly an X1, X2, X3 component. I can make a linear combination. I'll just call it W4 so as not to confuse it with the other ones, but W4 could be 2 times V1 plus 1 times V2. Okay, and that would look like this: 2 times 1, 1, 6 plus 1 times V2, 0, 1, minus 3. I go ahead, moving across, I add up the 2 X components. I get 2 plus 0, and I get 2. Then I get 2 plus 1, and I get 3. And then I get 12 plus minus 3, and that gives me 9. So there, W4 is a linear combination of V1 and V2 now in R3. And again, we will do this in later lectures as well, but you can see how I could easily scale up to R4, R5 just by simply increasing the number of components in the vector. Okay, vector equations of lines. Here's where it starts to get probably a little bit new notation that you may not have seen before. So a line through the origin in R2 is a set of the form. So this is telling me it's a set. This little set here is of the form T times the vector D, such that this little vertical bar here means such that T, and this is a set inclusion. So this means such that T is in R. Is in. So this this symbol right here, this guy here, T D, such that T is in R. Let me just read it in its set. If in its entirety, I see that. If I see that, I say to myself, oh, the set of all vectors T times D such that T is in R. And then at this point, D is not specified yet here, but then it says here where D is a vector through the origin. So that is a line through the origin, and D is a vector through the origin. Let's give an example. Imagine D here to be the vector 2, 1. Okay, so now I have a line. A line is all scalar multiples of that vector. Okay, so here I have a line. My line is T times 2, 1, where T is a real number. Okay. Just draw a picture. There. Here's the vector D. That's 2, and that's 1. That's the vector D. Now I imagine taking all linear combinations of this. That is, because I only have one vector, there's nothing else to add, but I take all linear combinations, which means I take all values of T, I multiply it by 2, 1, and I keep drawing them. So you can imagine when T is 2, you know, I'm out here. And then when T is 1.5, I'm here. And then when T is like pi, I'm somewhere out here. So I take all possible multiples of that thing and I keep drawing them. Right, and you can imagine all these points here. Each one of those corresponds to a different value of T. Here's for some negative values of T, like that. And the sum total of all of those is that line. It's the red line. So this is the vector equation of a line. That is the vector equation of a line that is through the origin. So we're going to now look at what does the vector equation of a line through a point, which is not the origin, look like. Okay, so how is my line going to look? Let me write it out and then I'll draw it. Here's a line that's not through the origin. My line is going to be equal to the set of all vectors 0, 3 plus t times 2, 1, such that t is in R. Let's make my R nice. Okay, what does that mean? That means I've got this thing right here. I've got the position 0, 3. So this is going to be 3 here. So I have a vector right here, 0, 3. And then I'm going to be adding all multiples of 2, 1. So I'm starting from here and I'm coming over 2 and going up 1. So I am there. There, for example, is when t is 1. And then I imagine when t is some other number, it'll be here, and then it'll be here, and it'll be here, et cetera, et cetera. So I will end up with all of the terminal points of my vectors in this set being on this line here. So that is a description of that blue line. Try taking a bunch of values of t so change this value of t. Make this calculation, draw those vectors, and see that the point of all of those vectors is on that line. So when I calculated, let me just make an example here for t is equal to 2. I want you to do several of these though, so you convince yourself of this. Let's take t is equal to 2. That gives me this 0, 3 plus 2 times 2, 1. And that gives me the vector 4, 3 plus 2, 6, 4, 6. So I come over here, 1, 2, 3, 4, and I go up here 1, 2, 3, 4, 5, 6, and I draw this vector. That is the vector, there it is. That is the vector 4, 6, and you'll notice that its point here is on that line. And that will happen for every value of t. So that is the set of all of those, the terminal points of all of those vectors is on that blue line. So that's how we define a line. Notice that this description here for the line does not have to always look exactly the same. Let me just give you an example. This is the same line. L, the same line, the same blue line, could also be described in this manner here. The vector minus 2, 2 plus t times 2, 1. Such that t is in R. Okay, ask yourself, why is that the same vector? Okay, and then what we're doing here is we're saying, let's take a look at what this is. Let's call that P. P is the vector going to minus 2, 2. So that is over here, 1, 2, 1, 2. Sorry, that's 3. 1, 2. Okay, so it is this vector right here. So all we've done is changed how we're defining one of the points on the line. Okay, so this point is on the line, and then when I add multiples of t, I'm going to still get that same blue line. You can see here, if I take this thing here and I wrote it as 2, 1 for t is equal to 1 plus some other number s times 2, 1. That means that s would be equal to 1 plus t, right? And then I took this and added it to this, I would get this. Okay, those are the same line. So you need to be able to identify when you have a vector equation of the line, whether you have the same line or not. So first of all, if you're going to have the same line, this thing is going to have to be the same. And then you have to determine whether both of those points are on the line. If they're both on the same line, then it's the same line. Okay, bit of a complication there, sometimes can lead to a bit of confusion. Okay, that was our vector equation of the line. Now we're going to take a look at another way of writing a line, which is parametrically. So let us just take the example from above, how we first had it. We had the line, and on the line that we had from above, the XY component was figured out in the following manner. From the vector 0, 3, we added all multiples of the vector 2, 1. Okay. That is our vector equation. So this right here is the vector equation of the line. Now we're going to write the same line and we're going to do it parametrically. And that is not hard to do. What we do is we go across on the top like that, writing that, and then we're going to go across on the second line. T gets to be in both like that. So that looks like this. X is equal to 2t and y is equal to 3 plus t. This right here is the parametric description of the same line. Again, you're going to have to remember and understand what the words mean. Vector equation of the line, parametric description of the line. And in this case, this is a parametric description and t is the parameter. Okay, you can see that each of you choose t and then x and y are forced to be something. So t is the parameter. Okay, and then now watch this. I was afraid to say that in case it goes wrong. Okay, what we can do now is eliminate the parameter and we will get the scalar equation of the line. That's the one that you're most used of. So let's just go ahead and do that. Let's take a look at this first parametric equation here and rewrite it like this, solving for t. So t is 1/2 x. I'm just dividing both sides by 2. And then let's take that and substitute for t here. So let me do that. I'm going to have y is equal to 3 plus t, but t is 1/2 x. And then let me just rewrite that by reordering the terms. Looks like that. There we have the scalar equation of the line. That's what you're used to seeing. It's the same line. Scalar equation of the line. You'll notice there's no vectors in the description and there is no parameter either. We've got two variables, x and y. There it is, scalar equation of the line, same line, parametrically described, same line described as a vector in the vector equation. I want to be able to go back and forth between the different forms whenever necessary, because sometimes it's easier to work with one form or the other. In particular, as we scale up into higher dimensions, this thing is not so good, right? This guy here, the vector equation of the line nicely scales to like 52 dimensions. So we're going to be moving in that direction. Okay, let's do the same thing here in R3. We basically repeat what we did in R2, and each vector has 3 components in R3. So our vector, we could have a vector v like this. Here's a vector v. We could be thinking of it as x, y, z, or we could be thinking of it as, this is just a labeling issue, x1, x2, x3. Okay, what does a line through the origin look like in R3? A line through the origin looks like this. It's all the vectors. All the vectors. So this is a line through the origin parallel to the vector 1, 2, 3. Okay, you know it's through the origin because there's no point. Okay, let me just there's no, okay, let me put what there is, and that'll be okay. Here's one that doesn't go through the origin. Line through the point -1, -1, 2, parallel to the vector 1, 2, 3. Okay, that I would write in this manner. Here it is. It goes through the point, and it is parallel to this vector here. So that's a line through the point. You can see here what I was trying to sort of point out earlier is there's just, you could be thinking of this as, well, let's just put it on this side, being like this. So we just don't write it. I mean, it is going through the origin, but when you add 0, nothing happens. So it's just missing. Okay, so there it is. So we can write down a line through the origin parallel to a certain vector, a line through a point parallel to a vector. And how do we write down a line through 2 points? Okay, so let's maybe change the color and think about this. So now I'm going to try to write out a line through 2 points. Let's just give 2 points. I'm gonna have to pick them. So I imagine I'm in R3, 3-dimensional. I'm going to give you 2 points. Let me just give you those 2 points. Here they are, 1, 4, 6, and 0, 0, 2. Those are 2 points in R3. What is the line through that goes through those 2 points? Okay, now I want you to imagine those 2 points in space. And then imagine drawing a line between those 2 points. Clearly that line will be, so I've got 2 points in space. I'm trying to put a line through it. I know it's in 3D, but here what we're doing is I'm trying to put a line through it. And then what I'm going to do is imagine this vector here. Clearly that vector is on the line. I mean, the vector connecting the 2 points is on the line. So when I write this out, I'm saying to you that what we have is this line is all the vectors x, which are formed in the following manner. Goes through one of the points. It doesn't matter which one I pick. Goes through one of the points, and it is parallel to the vector joining the 2 points. And the vector joining the 2 points is the difference between these two guys. So I'm going to write those numbers here, and then we'll just make sure we understand where they came from. Okay, where did this -1 came? Where did these numbers come from? Those numbers come from taking 0, 0, 2 minus 1, 4, 6. That is the vector joining the 2 lines. So the line through 2 points is, we write it as all the vectors going through one of the points, either one, that is parallel to the vector joining the 2 points. Those are lines in R2. Sorry, lines in R3. Okay, not only can we have a vector equation of a line in R3, but we can of course also write this parametrically. Okay, so let's just take the green example that we've been doing. This guy right here. There we have a line through 2 points. Let us just write that line parametrically. That is going to look like this. The parametric description here is going to look like this. X is equal to minus t. Y is equal to minus 4t. And Z is equal to 2 plus 4t. Okay, that would be the parametric description of that line. Okay, now you can also eliminate the parameter and get the scalar equation of the plane. Why don't you try that out? We're going to come back to that as well. Scalar equation of the line. Apologize. Okay, now let us take a look at a plane. So in R2, let me just, in R2, we're here like that, and we basically can have dots or we can have lines, right? We have a 2-dimensional object, and we can put into our 2-dimensional object, we can sort of draw a 1-dimensional object or a 0-dimensional object. Once we move up to R3, we can have a 0-dimensional object, a point. We can have a 1-dimensional object, a line, and we can also have a 2-dimensional object. For example, here we could have the XY plane. Okay, so now we're talking about the planes. A plane through the origin. The plane is like a piece of paper. So through the origin in R3, and what does it look like? So this is through the origin, it looks like this. All vectors of the form t times vector u plus s times vector v, such that s and t are in R. And u and v are vectors through the origin. Okay, so that is the definition, the vector definition of a plane in R3. Let's take an example. U, here's a vector in R3. U, it's 1, 3, 2. And here's a vector in R3, V. These got 3 components. Okay, then the plane containing these 2 vectors, is t times 1, 3, 2 plus s times minus 1, 4, 2. You can see that when s and t are both 0, you get the point at the origin. This plane goes through the origin. Okay, this goes through the origin. Okay, if we want a plane through a point, so here let's now scale up a little bit. A plane through the point through the point 1, 1, 1, containing vectors u and v is this guy here. It goes through the point 1, 1, 1, and it is parallel to vectors 1, 3, 2, and vector minus 1, 4, 2. Now, I'm going to use some more vocabulary here. This is just an introduction to it, but this is going to come up, and it comes up even in engineering right away. You will see here that we've got 2 parameters. 2 parameters. Okay, there are 2 things that we can independently change. I can change t to whatever number I want, and then independently I can change s to whatever number I want. Okay, sometimes in engineering that will be called, we will say we have 2 degrees of freedom. We have 2 things that we can freely choose, and one doesn't rely on the other. So this is the more engineering way of saying it, 2 degrees of freedom. You will notice that this is a 2-dimensional object. Like a plane is a 2-dimensional object. There's 2 degrees of freedom. There's 2 parameters. It's 2-dimensional. So immediately when you see an equation like this here, all the vectors x that are of this form, you're like, if I consider all the vectors x of this form, what does it look like? You look at it, you're like, there's 2 parameters. It's a 2-dimensional object. It's going to be a plane. Done. Okay. However, there is one small complication. This 2 thing relies on the fact that u and v are different enough. For example, if u looks like this and v looks like this, then we really don't have 2 vectors that are different in some sense, right? Because v in this case is simply 2u. So then I do not have a plane. I would simply have a line. If I was to write out all the vectors x of this form, t times 1, 2, 3 plus s times 2, 4, 6, I don't have a plane. Even though it looks like there's 2 parameters, there isn't really, because what I can simply do is say, okay, hang on, let me just change this to 2t, taking out the 2 and put this as 1, 2, 3. All right. And then I can just simply add together. Okay, so you have to be careful, and we're going to see that we have a word for this. It's called linear independence. Okay, I'm having my Zoom Wi-Fi on my laptop here. Zoom has disconnected. Hang on, just give me 2 seconds to try to get that reconnected. Share screen. It looks like things are going to happen again here. Share screen. Sure. Just wait for 2 seconds. Okay, I'm back. Okay, so I lost the Wi-Fi connection to my tablet momentarily there. Okay, so here's a question. Is R2 a subset of R3? I'm giving you some time to think about this. Is R2 a subset of R3? Okay, hopefully you've made a commitment. You should make a commitment, because if you're wrong, you'll remember. And if you're right, you can congratulate yourself. Either way, it's better to make a decision and then wait for the answer. Okay, so the answer here is no. Okay, no. And the reason for that is R3 looks like this. It's a pile of infinite amount, actually. It's a pile of vectors that all have 3 components. 1, 1, 0, for example, is in there. It doesn't matter. There's gazillions of these things, right? -0.5, 4, 6. They don't have to have all pi, e, and 10. There's an infinite supply of 3 component vectors in R3. What does R2 look like? R2 is an infinite supply of 2 component vectors. Yeah, and there's an infinite supply of those guys. Now we're asking, are these guys a subset of these guys? Which means, can I reach into this bucket? Can I reach into the R3 bucket, this guy here? Can I reach into the R3 bucket and pull out these guys? No, I can't. There's no guys in here that have 2 components. So I cannot pull out this guy, for example, from in here. He's not in there. So R2 is not a subset of R3. Okay. All right. So then the next thing we've got here is a variety of exercises. Please, please, please try the exercises. You've just listened to the explanations. And then if you try the exercises and you cannot do them, then maybe look back in the lecture, read the textbook, and then come on to the Zoom session for this lecture, and we will discuss whatever you like about the lecture. We can also do some of these questions together and make sure that the material that we've just gone over, which does allow us to answer these questions, is understood. And keeping up is key. Okay, thank you very much, and I'll be back with the next lecture shortly.